hopefully you can remember from the past 2 weeks that we've essentially been looking at how we can represent azeotropic distillation systems on ternary diagrams, and how we can use what are called residue curves to actually represent those systems. So hopefully from the tutorial questions, you kind of have an idea how we can either plot these residue curves accurately using exact information about the vapor-liquid equilibrium between all our components, or if we have just knowledge of the compositions and the temperatures of the azeotropes and the pure components, that we can actually look into creating an approximate set of residue curves, or at least find out where our distillation boundaries are. So what I want to move on today is actually, so now we have these residue curves. What can we actually use them for? So what are the use of these residue curves? And also, what methods do we have of actually separating components with azeotropes in? And then how can we use these ternary diagrams to actually start to represent these distillation sequences so that we can actually think about designing the separations for these azeotropes? So as I mentioned before when we started to talk about residue curves, that actually the feasible distillation regions for some of these ternary mixtures are not actually that obvious. So these residue curves actually allow us to make an estimation of what separations, what feasible compositions we can actually get in a separation from our distillation column. And these regions, essentially what we do is we look at doing a mass balance line for our distillation columns. Okay? So as I mentioned, and exactly the same when we looked at liquid-liquid extraction, because we've got a sequence that is essentially a mass balance, we can actually represent that with a straight line. Okay? So because our mass balance points are essentially our distillate composition and our bottom product composition, we can have a straight line that passes between the distillate and the bottom product. Okay? But it also must pass through our feed composition, because that's what we add into our system. Okay? So if you remember when we looked at liquid extraction, we had our feed added and our solvent added, were joined on a straight line, and then the mixed point composition had to lie on that line. So in this case, we have our distillate product and our bottom product joined with a straight line, and our feed composition has to lie on that line. Okay? So we also saw that our residue curves are actually related to the actual vapor-liquid equilibria. So you can think about that as the actual stages in the distillation column. Okay? So that means, because our distillate and our bottom products are also defined by that vapor-liquid equilibria, it means that the ends of our straight line that we draw for our column mass balance must also lie on one of these residue curves. Okay? So in that way, we're satisfying both the mass balance for the column, but also the fact that we're doing a separation based on vapor-liquid equilibria. So let's have a think about one of these systems. So this is a simple... Oh, that was exciting. Okay. It was a simple Azeotropic system. So these are our residue curves, and if you remember, pointing in the direction of the higher boiling component. Yeah. So let's think about this feed position. Okay. So what I just said is that through this feed, we can draw a straight line, and the ends of that straight line represent the top and the bottom products of a distillation column. But they also must lie on the same residue curve to satisfy the equilibrium. Okay? So if we think about that we've got a specification for a distillate product that's here, so what we want to do from this is find, well, what's the composition of the bottom product? Okay? So we can use those two pieces of information and say, right, well, we know that our bottom product must lie somewhere on this same residue curve. Okay? And we can also say, well, our bottom product must also lie on a straight line that passes from the distillate through the feed. So where that straight line meets that residue curve, we can actually define our bottom product. Okay? So that very simply allows us to actually draw our distillation column, and if we have a specification for the distillate, we can quite quickly find the composition of the bottom product. And if you think back to liquid-liquid extraction as well, we could use the lever arm rule on the points on this straight line to actually find the total flow rate of our distillate and the flow rate of our bottom product. Okay? So if we change the specification of our distillate, then obviously we get a different specification for our bottom product. Okay? And if you think about this, for a given feed, there is a large number of these straight line mass balances that we can make for different columns, depending on what we specify either our distillate or our bottom product to be. Okay? So what we can do is we can take that idea and actually think about, well, what are all the possible combinations we can possibly have? Okay? So if we think about all the possible combinations we have, essentially what we're doing is specifying for a given feed, well, what separations are actually possible. Yeah? So it allows us to see if what we actually want as a product we can actually get. Okay, so let's take our same feed and our same example again. Okay, so let's think about an extreme. Okay, so an extreme potential product is actually taking our low boiler. Okay, so all our residue curves are passing this way. So essentially we'll say, well, what if our distillate composition starts at the start of our residue curves? Then what we get essentially is a bottoms product that can lie right at this extreme side. So if you think about it, we're essentially following the residue curves that start here and they come around and they come down this axis. So they're lying essentially on what we can almost think of as our extreme residue curve, which actually is this axis of the ternary diagram if we follow those arrows. Okay? So we can also think about, well, what's our other extreme? Okay, so our other extreme is that we define our bottoms product to be essentially the product that we get at the end of all our residue curves. Okay? And if that's the case, that gives us a distillate down here at the bottom. And again, you know, we're thinking about that residue curve that goes all around the outside. Okay? So that's essentially our two extremes. What we also want to think about is actually the residue curve that passes through our feed point. Okay? So that's the residue curve that our feed point lies on. Now, if we think about this, and we think about where we can draw our possible lines that still satisfy lying on the same residue curve, but also passing through the feed, what we get is these two regions. So what we've done is we've got on the outside of our residue curve, and then we're limited by our extreme in terms of our distillate product. And in this case, we've gone on the outside and we're limited by the extreme of our bottom product. And if you think about, if we pick any distillate composition in this region, we can always draw a straight line that passes through our feed and goes to the same residue curve. Okay? But if we're outside these two green regions, it's actually impossible to draw a straight line that satisfies a straight line that passes through the feed, and also both ends lie on the same residue curve. Okay, so for instance, if we were to start at this point here with our distillate on this residue curve, so we know that our straight line must also end on this same curve, but must pass through that feed point. Okay, and that's physically impossible to do without drawing a curved straight line. Okay? And this essentially is our feasible region of distillate compositions, and this is our feasible region of bottom product compositions. Okay? So this brings us back to that essentially very first example with the azeotropic distillation, where I started to draw the different distillation options on, the direct and the indirect sequence. Okay? And we said that there's only those two options. We couldn't actually have the third option, which was separating the intermediate boiler off first by itself. And you can see that our low boiler, which we could separate off from our feed, is actually in our feasible distillation region. Our heavy boiler that we could separate off is in our feasible region. But our intermediate boiler that originally we just knew from our knowledge that we couldn't separate off by itself is actually outside of our feasible distillation region. Okay? So those green areas are the only feasible products that we can get for that particular feed. Okay? So if you want a product that falls outside of those green areas from your particular feed, it immediately tells you that you need more than one distillation column to undergo that separation. And because of the shape, these green regions are often called bow tie regions, so you might see them referred to as bow ties, because they look a bit like a bow tie. Okay? So what we can do is actually, well, we can think about this now for a much more elaborate system. Okay? So let's think about our feed one. Okay, so it passes through, quite conveniently passes through this residue curve, or in this case, they're actually distillation curves, because you can see the arrows are pointing to the low Boiling, yeah. So we've got our feasible project based on the extreme bottom product. We can also draw based on our extreme top product or distillate. Okay? And then here's our key residue curve. And again, we can think about, well, what is our space above our residue curve to our extreme distillate, and what is our space between above our residue curve and our extreme bottom product line. Okay, and again, we generate our two feasible product regions. But in this case, what you can see is because we've got this distillation boundary, our extreme bottom product line stopped at that distillation boundary because all our residue curves curl around up this boundary. So if we go past this boundary, we wouldn't be on the same residue curve. Okay? So it backs up when I said before, we can't cross distillation boundaries. Okay? So this helps to explain why you can't cross distillation boundaries, because in this direction here, there's essentially no change in the vapor-liquid equilibrium, so there's no ability to drive you across here, and all our distillation curves swing round and follow this. Okay? And if we want to, we can also repeat this exact same process for this feed 2 up here. So again, we can think about our extreme bottom product and our extreme top product. Okay? So again, we're going a straight line for our feed, and we're following our extreme residue curve, which goes round here. We now have a slightly more interesting shape residue curve passing through our feed point. But again, we still go in the region between our residue curve and our extreme distillate line to get our bottom product region, and we still go between our residue curve and our extreme bottom product line there to get our distillate region. Okay? So if we have our F2, the only feasible products we can have are in those green areas. Okay? So this then brings us on to thinking, well, if we can now represent our distillation systems, and we can now also look at what feasible products and feasible separations we can actually do based on our vapor-liquid equilibria and our feed point. So what we now need is to actually, well, what potential solutions or what potential options do we have to actually use to separate azeotropes? Okay? So if we go back to our original thoughts, so well, if we've got two components and we've got a binary azeotrope, so I mentioned that we could hope that potentially, if we can change the pressure and it moves our azeotrope, okay, we might be able to move it enough to actually still allow us to do our separation. Okay? What we also might be able to do is, if it potentially doesn't move enough to allow us to do our separation in one distillation column, we can actually use the moving of the azeotrope in terms of composition to our advantage, and actually use that to try and skip over our azeotrope. So what we would actually do is look at two ordinary distillation columns, but at different pressures, okay? And that would allow us to essentially try and move around that azeotrope. The disadvantage is obviously, because we've now got two distillation columns, and they're at different pressures. So we need some kind of pump or compressor to actually increase the pressure between the columns. And then, when we come back to the first column, we would actually just need to reduce all that pressure back down, okay? But an advantage is that we don't need a third component in the system. So let's have a look at what I'm meaning by saying, well, if we can use pressure to take advantage of moving our azeotrope, okay? So if we just start off thinking normally about our distillation, we've got our feed composition that we're adding into our first distillation column, okay? And then we get a separation in our distillation column, which we can see on this temperature composition diagram, okay? So if you remember, our bottom line here is our bubble point, and our top line is our dew point, and then where they meet is our azeotrope. Yep. So we can achieve a separation in our first distillation column, essentially near where we want of our pure component B, but our composition of component A is now essentially stopped by our azeotrope. We can't jump over that azeotrope, okay? So that allows us to take off our bottom product that essentially meets our specification of component B, but then we're stuck with a top product defined by our azeotrope composition. But if we change the pressure now for our feed into our second column, okay, so what we've done here is we've actually increased the pressure. Yep. And if that change in pressure moves the position of our azeotrope, yeah, we can now take advantage of that. So if we now move to our second column at a higher pressure, what we've done is we've moved the composition of our azeotrope. So now what we find ourselves in is we did have products only in this large region of our system, but now we suddenly have a composition that's inside our other region, our smaller region, where we can get essentially a product that's pure A. Yeah? So now all we do again is simple distillation again, but based on our separation here. And then what we get is our bottom product that can meet our specification of pure A, and a top product that now is defined by the composition of our azeotrope at that different pressure. Okay? And instead of just wasting that azeotrope, all the material that's in there, we can recycle that back round to our first column, and then what we can do is we can put that back into our first column higher up, where the composition on a particular stage inside our column is quite similar to the composition of the material that we're returning. Okay? So what we've done there is we've just simply used the fact that if we change the pressure, we can move our azeotrope back and forwards in terms of composition to just jump around our azeotrope. Okay? So although that's a great option to use and is actually widely used in industry, the problem that we have is that we actually need an azeotrope that moves with pressure. Yeah? So as you saw, it needs to move really in excess of about 5% in terms of composition over a moderate range of pressure, only a few bar. Okay? And the reason for this is that if you need to start increasing the pressure a lot, maybe 10 times the pressure, 20, 100 times the pressure between the columns, it then becomes far too expensive to be actually a viable technique. And if the composition of the azeotrope doesn't move very much, then the difference between the feed into the second column and what you're returning into the first column isn't a lot, yeah? Because essentially it's just the difference between the two azeotrope compositions. And if that composition is very similar, what you end up with is that the recycle loop around between the columns has to have a very, very high flow rate, okay? So you're recycling loads of material through the columns, so your flow rates through the columns are a lot higher than essentially the amount of products that you're producing. So it then costs a lot to pump that material around, heat that material to vaporize it, compress that material to change the pressure. Okay, so again, it becomes essentially economically unviable. And in that case, you essentially need to think about, well, a different technique. So, because we've got these essentially very non-ideal components, because we have to have non-ideal components if we have an azeotrope in our system, it generally means that those components have very different affinities. Okay, so their solubility parameters are very different. Yeah? So in liquid-liquid extraction, we took advantage of those differences in solubility parameters to actually add another component that preferentially dissolved one of those components based on that difference in solubility. But in this case, what we can do is we could think, well, if we add a solvent, maybe that solvent isn't good enough to undertake liquid-liquid extraction, or maybe liquid-liquid extraction isn't suitable for other reasons, potentially such large flow rates, or it would take so many stages with liquid-liquid extraction, it's not viable to do. But we can think about adding another solvent. And the addition of that solvent essentially can affect the vapor-liquid equilibria between our two original components. So ideally, we'd want to add a solvent that doesn't form an azeotrope with any of the other two components already in our feed. Okay? And normally, for something like this, to actually have enough solvent to cause a big enough change in the vapor-liquid equilibrium of the two components we want to separate, we at least need a solvent ratio of the same order of magnitude as the flow rate of our feed going in. Okay, so we need actually quite a lot of solvent, quite a lot of material added to our system. And then what we can do is we can essentially process our bottom product to recover the solvent back from our system, and then we can actually recycle this solvent and use it again. Okay? So if our feed is a minimum boiling azeotrope, what we generally want to do is try and add a solvent with a lower volatility than our key components. Okay? So we want a solvent essentially with a very high boiling point. And then what that allows it to do is us to recover it in very high efficiency from the bottom of our distillation column. But also what it means is we can add it to the top of our column, and then because it's got such a high boiling point, it'll essentially flow down our column and will hardly vaporize in our column. And if it's a maximum boiling azeotrope we have, essentially we do the same, we still want the same qualities in that solvent, generally something with a very high boiling point, but we would generally add that in with the feed rather than the top of our column. Okay? So I like to think of the potential for this extractive distillation in two ways. Okay? So if we can find a solvent that we can actually add to our system where the boiling point is so much higher than the boiling point of the two components that we're separating. Essentially in our column, that component that we're adding basically never boils. The vapor-liquid equilibria for that component, because its volatility is so low and it's got such a high boiling point, that the composition of that component in the vapor phase is always so small, we can essentially ignore any vaporization of that component. And if that's the case, we can essentially view, well, that component doesn't actually take part in the distillation at all. It just flows down the column as a liquid. Yeah? But what it's doing is it's just changing the relative volatility between the two components we're trying to separate. So I think I promised at the start of the course we would look at a method of how we could separate ethanol and water by distillation. Yeah? So here it is. So if we add ethylene glycol to our mixture of ethanol and water, the boiling point of our ethylene glycol is much higher than both of these two materials. So essentially it just flows as a liquid down our first column. But what it does is if we have no ethylene glycol, we get our vapor-liquid equilibria for our water and ethanol as the non-dashed line, and we have our azeotrope. But if we add our ethylene glycol, that affects that relative volatility. And what it does is if we to plot the new vapor-liquid equilibria between our ethanol and our water, but in the presence of ethylene glycol as a liquid, we actually get this dashed vapor-liquid equilibria curve. Okay? And you can see there that actually the azeotrope has completely disappeared from our system. Yeah? And we've now got essentially a vapor-liquid curve we can quite easily carry out distillation with. Yeah? So what we can do is take our distillation column, achieve our separation and get our ethanol as our top product, and then we can get water as our bottom product, but all the ethylene glycol essentially comes out with our bottom product. So we can then just go into a second distillation column where we then just carry out distillation between the ethylene glycol and the water, and then we recover our water as our top product, and we just get our ethylene glycol as our bottom product, which we can then recycle back into our first column. Okay? So in that case, we're just taking advantage that the solvent changes the relative volatility between our two components, okay, but doesn't really take part in the actual separation in the first column. So the second example for extracted distillation is where actually picking that solvent that has such a large difference in boiling point isn't possible. Okay, so you might be able to find a solvent that works that you can add to your system, but it doesn't have that huge difference in boiling point. So what that means is when you're actually undertaking the distillation, that you can't think of that component as always being a liquid. It will vaporize itself. Therefore, you actually get a split of that component potentially between the top and the bottom of the column. Yeah, and that component vaporizes on the different stages, actually taking part in the equilibrium. So in that case, we have to actually think about our whole system as our ternary diagram system, okay? But we know that we can use this and the idea of our residue curves to actually look at that separation. Okay? So very typically, what we have when we have extractive distillation in this case is we have this 3 distillation column system. Okay? So there's essentially 2 main forms. There's a 3 column and a 2 column form. But we're going to look at the 3 column form here. So if you have a 3 column form, what you do is you think, well, we've got our feed and we're trying to get pure A and pure B from our system. But you can see we have an azeotrope here that's essentially blocking us from getting pure B directly, okay? But what we can do is we can just run a normal distillation column and we can get essentially some pure A from our system, and then we can get a composition of our distillate near the azeotrope, okay? So the reason that we do that is because that's simple for us to do, and it gets some of our feed out of our distillation sequence as early as possible. Yeah. So when we're looking at the stage that has a recycle with the solvent in, we don't have such a high flow rate of material needing to be put in that system. Okay, because we've already extracted one of our pure components that we can actually get to. Okay, and that's the reason that this first column is often called a pre-concentrator column. Is that, yeah? Yeah. So we can draw all of these columns on this diagram, yeah. So you've preempted the next. So our first step is essentially we can do our first column. So the next thing we do is, well, now we need to think about adding our solvent into our system, yeah? So we know, and you remember from liquid-liquid extraction, that if we have a mass balance, it's a straight line, yeah, as I keep saying. So all we're doing here is at this mixing point, we're adding pure solvent to our distillate from our first column, okay? So if we draw a straight line between our pure solvent composition and our distillate composition, what we know is that this combined F2 composition must lie somewhere on this dashed green line, okay? Now what we need to think about is our second distillation column, okay? So what pure component do we need to take out of our second distillation column? Okay, so we have to think about our feasible regions, yeah? So if I was to say, okay, so our product from our second distillation column, we're going to get some pure A, okay? What we would need to draw is a straight line from pure A, okay, that passes through our dashed green line, because we know somewhere on that dashed green line is our feed into that column, okay? And then comes to a bottom product where the two ends of our straight line lie on the same residue curve, okay? So if I start here and come down here, so that's our top product and our feed, I need to lie on this same residue curve that A is on, but there isn't. Yeah, it's impossible to be on the same residue curve because the residue curve just goes around the outside. So unless I just go down this line here, which essentially means that I've added so much solvent into the system that it's pure solvent, okay? So you can't actually do a separation for this second distillation column and get A as our component, okay? So does that make sense, yeah? Based on, I can't draw a straight line on the same residue curve, yeah? So that leaves me with the option of, well, can I get B? Yeah, so can I get B as our pure component? Okay? So if I think about coming down here to B, I can see there's this residue curve here that's very close to getting pure B. Okay? Oops. So I could think about putting a distillate product down here, yeah? But what I need to do now is think, well, can I draw a straight line that lies on the same residue curve? And that residue curve comes all the way down here to S, that passes through this green line. Well, yes, I can. So one example would be this red line. Yeah? So you can see that our distillate composition is near our pure B. And if I come over here to a bottom product, it lies on the same residue curve, and it also crosses our dashed green line, which is where we know that our feed to that column must be on. So we know that our feed composition to our column must be where those two lines cross. Okay? So now what we could do is we could use the lever arm rule if we wanted on our dashed green line to find out the flow rate of solvent that we need, okay, compared to the amount of our distillate to feed into our red column. Yep. So now we can think about adding our third column onto our diagram as well. So the only option is to get pure A from the top, because we now have pure B coming out, so we want to get the remainder of our A. And what we can essentially do is go along the residue curve that flows along the outside axis of our diagram. And it allows us to recover our pure solvent as our bottom product and A as our top product. Okay? So what we managed to do is to draw our whole distillation sequence, including our mass balance for the addition of the solvent, just using our ternary diagram, okay? And not only have we managed to design our sequence using our ternary diagram, we can read off our diagram the composition of every single stream in our sequence, and we could use the lever-arm rule on all of our separations to find the flow rate of every single stream in our distillation sequence. Okay? So can you see how valuable that is as something we can do? Yeah? Because as soon as we know the compositions and the flow rates, we could then design each of these distillation columns using the shortcut method, okay, to actually get an estimation for the number of stages and the reflux ratios needed for those columns. Yeah.
Where would the solvent be adding to the system initially? So I don't think the second column, where would you need to turn into second B, would be
In reality, you would probably put the solvent. Well, okay, so it depends. So as I mentioned, if you have a minimum boiling azeotrope, you tend to put it in at the top, physically at the top of the column. But if you have a maximum, you would put it in with the feed. But it makes it a lot easier for drawing on our diagram if we mix it in with, no matter where we actually physically put it in the column, we mix it with the feed first, because then that allows us to define that mixing line. Yeah. So I want to move on just to the final few options for azeotropic distillation. So far in the sequences that we've looked at, the two methods we've looked at, the extractive distillation and the pressure swing distillation, we've actually been quite lucky, because we've either managed to find an azeotrope that moves quite a lot when we change the pressure a little bit, or we've managed to find a solvent that we can add to our system that doesn't form an azeotrope with either of the components that we already have in the system. Okay? So both of those options would actually make us pretty lucky to actually be able to find that. So if we can't find that, you know, we may be able to say, well, actually, what if we can pick a solvent or an entrainer that we add to our system that doesn't actually have that specification, that it can't form an azeotrope with any of the other components? What if we say, okay, well, we'll allow it to form an azeotrope with one of those components? Can we still work with that to actually get our separation? So instead of essentially recycling the pure solvent or the pure entrainer, we can say, well, what if we think about recycling the azeotrope that entrainer forms with one of our components? Can we still get away with that as a system? So if we have this slightly more complicated system, you might recognize it from last week, from the approximate residue curve drawing tutorial. Sorry, from the example in the lecture. So we're trying to separate our A from our B based on our feed F. But we've got an azeotrope in the way. And we managed to find an entrainer or a solvent that we can actually add to our system. But unfortunately, that actually forms an azeotrope with our A. And we also have this other interaction with both our components to form as a ternary azeotrope. Okay? So it adds to the complexity that we now have these two distillation boundaries within our system, but can we still actually design a system that we can use? Okay? So for this example, I've done away with the third column, so the pre-concentrator. So we're just going to have a look at thinking about designing a 2-column distillation sequence. So this choice of whether you use a pre-concentrator or not is essentially a design choice that you have to make. So when you come to designing the separation, you might think about both options, okay? And then you can look at the economics of both options and think about whether that pre-concentrator makes your sequence cheaper or not, okay? So as a rule, the closer your feed is to your azeotrope point, the more likely it is that having a pre-concentrator is not going to be as effective, because you're actually removing a lot less of your feed out of your system at the start. Okay? So let's think about our system. So, as I say, we can't add, if we had pure entrainer, we can't actually, from our feed, because we've got this distillation boundary, we can't get to pure entrainer. It's not a possible composition that we can actually get, not a possible product. But what is possible actually is this azeotrope between our component A and our entrainer. Okay? So we can think about, instead of recycling this pure, well, what if we recycle this azeotrope? It's got quite a lot of entrainer in anyway. We're recycling it so we're not losing it from the system. So if we're recycling this and adding this to our feed point, then we know that our combined feed into our first column, again, must be somewhere on a straight line between the azeotrope that we're recycling and our original feed point. Yeah? So if we then come to look at our our first column in this case, we're being told that our bottom product is B and our top product is a mixture of A and E. So what we need to do is essentially think about, well, can we have a straight line that joins our bottom product to B to what we want in our top product, which is obviously something that has as little of B as possible, so as much over here as possible. Okay, so a straight line between those two positions that passes through our dashed green line and where those two ends of the line lie on the same residue curve. Okay? So we can see that if we're going towards B, all these residue curves come like this and go into B. So if we think about the most exterior of our residue curves, which is the one that essentially uses the axis in our distillation boundary, then we can specify this as a potential line. Okay? So we picked out B. We know that our top product here lies on the same residue curve, and we can see that it crosses the line. Okay? So we can then think about our second distillation column. So we already said we're recycling this AE azeotrope, so the bottom product must be the AE azeotrope, and we want our A component from the top of our distillation, so we can specify using this axis here. So what we managed to do is, even though we can't use a pure solvent, we've still managed to separate and get our pure A and our pure B using this entrainer. So I just wanted us to think back about when I added this line for our first distillation column. Yeah.
How did you add that resin? Like, is it given that we know A and B?
So this is what I'm, yeah. So, so when we add this line, we knew B, yeah, but we didn't necessarily know the A to E composition, yeah. Now this is where your design decision comes in, and also you can think about optimization, yeah. So what I could have done was drawn this line lower, right? So essentially a more shallow line. And what that would have done was it would have crossed the dotted line here closer to our feed composition, yeah? Or I could have drawn it more up here, and it would have crossed this line much closer to our azeotrope composition, okay? Now, if I'd crossed it up here, much closer to our azeotrope composition, that would mean that the feed into this column would contain a lot more of our azeotrope, yeah? Which would mean that we will be recycling a lot more of our azeotrope around our system. So we would have a lot more entrainer in our system, and we would be recycling a much higher flow rate, yeah? If I bring it down here, we would have a lot lower amount of azeotrope in our system, and we would be recycling a lot of a lower flow rate through our system, yeah? So you might think the lower the better, yes? Because that would mean that we need a smaller system, okay? Which is a possibility. However, we don't necessarily know how easy this separation is until you actually do the calculation for the reflux ratio and the number of trays that we need, okay? So what we can see is, although it's allowed us to design this system, we've got essentially a design choice, and that design choice is how much solvent that we add, how much of our entrainer do we add. So we have to balance that off against the cost of running our distillation column and the cost of adding our entrainer. So it's another, so just like we would balance off number of trays versus reflux ratio versus utility cost, yeah, we now have to think about number of trays versus reflux ratio versus utility cost versus amount of entrainer that we add to assist our system. So it's another optimization that we have to think about, okay? Yep. So these don't allow you to do that optimization. You actually need to do the design, but they allow you to design, yeah, because no matter where this line, if this line's up here or this line ends down here, it's still the same design, yeah, okay? So for a distillation system to actually have this nice homogeneous style azeotropic distillation that we can use, often what we actually need to generate the curds that look like that are one of the azeotropes to be maximum boiling, okay? But unfortunately, minimum boiling azeotropes are much more common in systems, okay? So we essentially need to actually think about a different system, so we might not be able to actually use this homogeneous azeotropic system, okay? So if you can see, what I've been doing is actually thinking about, so essentially we're increasing the difficulty of the separation as we go through. So pressure swing would be a good option if it's possible. Then if that's not possible, you might think about just adding an entrainer when no azeotropes are formed. If that's not possible, you say, okay, well, we'll allow it to be a maximum boiling azeotrope. And if that's not possible, we go, oh, well, okay, we're going to have to cope with just what we can do, okay? And what we might have is that the entrainer forms a heterogeneous azeotrope. Okay? So now we have the fact that at some point in our system, we have a vapor in equilibrium with two liquid phases. Yes? So we have vapor, liquid, liquid equilibrium. But we can actually take advantage of this, because if we have two liquid phases, we can actually take advantage that if we condense a vapor that forms two liquid phases in equilibrium with each other, we can actually get some separation by those two liquid phases being at different compositions. Yep. And this brings essentially a unique opportunity to us. So one of the issues we have is our distillation boundaries that we can't cross. We can't cross distillation boundaries with distillation, yep? But we can cross distillation boundaries with a different type of separation. Yep? Liquid-liquid separation, the equilibrium separation of two liquids, is a different type of separation. Yep? So potentially, that gives us the advantage that we can actually cross distillation boundaries because we've got that different type of separation in our system. And also, it's quite often the two liquid phases we get, if we just let them settle into a decanter, then they'll form those two liquid phases just by gravity. So actually, it could be a very cheap separation as well. So essentially, as I said, because we've got that opportunity to potentially now jump these distillation boundaries, not only do we have that opportunity, but actually typically the liquid phases lie in different regions of our diagram, okay? So it means that we can actually jump around the problem that we have with the homogeneous azeotropic distillation, that we can't get a pure component, and actually use this to our advantage. So what we can do is we can actually separate components that don't lie in the same region. So even if we've got a system where we can see a distillation boundary and we have components that we want as pure components that lie on different regions, this is a technique that we can think about straight away. Okay? So this is an example of such a system. So we've got our component A and B, and you can see that we have our azeotrope between them, and we have our entrainer or solvent added, but we've got a distillation boundaries that are essentially blocking off the region where we can get pure A from the region where we can get pure B to the region where we can get our pure entrainer. But we do have this heterogeneous ternary azeotrope here, and that has a liquid-liquid separation that follows essentially this tie line. So if we have a liquid here, we would produce one up here in this region and one down here in this region. Okay? So again, we'll have a think about just a two distillation column sequence for this separation. I thought I'd fallen over them. But what we've got is we've got a lot of areas actually on our thing where we have columns with multiple feeds. Okay? And as we mentioned when we were looking at our extractive distillation column, it's much easier to us to actually think about doing the addition as its own step, separate to doing the separation with the distillation column, okay? So what we can do is just modify what we would build in reality system into a more simplified distillation sequence where our addition steps are essentially done separately to our separations. So the first part is here. So you have your condenser that forms your liquid into your liquid-liquid separation. And then you take one of your liquids to one column and one of your liquids to the other column. Okay? But you also take some of both liquids to your column to get that reflux. Yeah? So what we can simply do is just change this into a concept where, well, we have the standard reflux model, and then what we don't reflux, we actually separate. Okay? And that allows us to simplify this into a standard distillation column, followed by a simple liquid-liquid separation. We then have this situation where we essentially have one feed into the column plus the feed of our extracted liquid return. Okay? So again, we can simplify that by essentially doing that addition before the column, so we only have one feed. So we just add the distillate from column 1 to our X-rich liquid before we add it into the column. Okay? It doesn't actually affect the separation or the mass flows. It's just a way of drawing this system better so that we can actually represent it on our ternary diagram. We have the same issue with our column 1, that we have our main feed into the whole system, and we then have our X-lean flow. So again, we can just sort that, so we add that to the feed before we go into our column. Okay? So now when we're trying to design this on our ternary diagram, we can think about our more useful sequence for us. Okay? So let's take this F1 as an example of a feed that we're trying to separate. Okay? So we've got our mixture of A and B that we're trying to separate, and we can't get that because we've got our azeotrope in the way. Okay, so we found an entrainer that gives us this horribly complicated system. Okay, but it's the only entrainer that we've actually been able to find that allows us to do any type of separation, so we go with it. Okay? So we now need to start thinking about, well, what do we know about our system that we can start to draw on our ternary diagram so that we can start looking at what we can add together. So the first thing that we mention and what we try and do with heterogeneous azeotropic distillation is to mention that the one where we actually come to our heterogeneous azeotrope, we try and get our top product composition to be as close to that heterogeneous azeotrope as possible. Okay? So what we want to do, what we can do, is we can actually say, well, if this top product composition is exactly that ternary azeotrope, what would we get? Okay? So later on, after we've done this, we can potentially slightly move this composition to one that we can get to. But as a good start, let's start from that ternary azeotrope composition. Okay? So what's the advantage of actually making that making this product here the ternary azeotrope composition. Okay, so the reason that we do that is it's actually the only point on the diagram that's accessible from every region. Yeah? So this azeotrope here, we could come to it from this region, we could come to it from this region, or we could come to it from this region. Yeah? So it gives us that flexibility to design to this point from anywhere on our ternary diagram. Okay? So we know that if we've got this then, based on our liquid-liquid equilibrium information, we generate two liquid products from that vapor, one of which we can define as A-rich, and one of which we can define as A-lean. Okay? So now we need to think, well, what do we do? So we can actually join our A-lean up to our feed. Okay, so if we mix those streams together, what we know is that that combined stream must lie on that green line. Yeah? So then we pass that into our distillation column 1. And we've been told that our distillation column 1 produces a product of B, but it also produces another product that we essentially recycle to our feed of our other column. Okay? So what we need is to draw our straight line on here that gives us a bottom product of B. Our feed passes through this green line, and then we have a top product composition. Okay? So if we do that, we could draw a straight line essentially up here. Okay? And now what we're trying to do is, if we're getting B here, we want our distillate to essentially have a smaller amount of B as possible in it. Okay? So the ideal would actually be to go up to our distillation boundary, yes? Because that would actually be the point where we would have the least amount of B in our system. But if we go right up to our distillation boundary straight away, it doesn't give us any flexibility in this position. Yeah? So as we spoke about, we're designing our system, but we still need to think about our optimization afterwards. So if we draw this point right up to our azeotrope and we find that we need to adjust it slightly with a slightly higher concentration of A, we then move into something that's impossible. Yeah? So if we stop just short, then that allows us to be able to adjust this point in essentially all directions rather than just one direction. Yeah? If we had residue curves drawn on this diagram, we would also need to make sure that our B and our D lay on the same residue curve. Okay? But we know for this system that we would essentially have residue curves that go like this. So they start here, go down to B, and they start here and go to B. Okay? The reason that I've not drawn residue curves on this diagram is that there'd be so many lines on the diagram that you wouldn't actually be able to track redrawing the distillation sequence on. Okay? So we've now specified the liquid-liquid step and our first distillation column. Okay? So we only have our second distillation column to go. So the next thing that we can see is, well, we take our A-rich and we mix that with our central top product from our distillation column 1. Yeah? So we take our A-rich composition, and we can join that with a straight line to our D1 composition point. And what we know, therefore, is the feed into our column 2 must lie somewhere on this top green line. Okay? Now we need to think about the separation in our second column. So we know that we need A from the bottom of our column, and we've already decided that the top of our column should be our ternary azeotrope. Okay? And what we also know is the only region that that's possible in is this top region here. So what we need to have is essentially a straight line that gives us a bottom product of A, a top product of the ternary azeotrope that passes through our feed point line. Okay? And hopefully that's possible. If it's not possible, we've not done it correct and we need to start again. But fortunately, it's possible. Okay? And we can now see the specified ratio point for F2. Okay? So what we managed to do is just using the same techniques all the way through of knowing that the distillate and the bottoms are on the same residue curve, and the distillate, the feed, and the bottoms all lie on the same straight line, we've managed to essentially start to increase the complexity of the systems that we're drawing on these diagrams. But as soon as we've managed to draw these systems on the diagrams, we can actually get all the information that we need to design the system, because we know compositions, because we can read them directly off, and we can find the flow rates because we can do the lever arm rule on all of these lines and get the flow rates for all of the streams. Okay? And then that allows us to use the shortcut methods to get an approximation for the design, or to go straight to something like Aspen and design the columns in full. Because the one thing that Aspen doesn't do and cannot do is it can't design the sequence for you. Yeah? So when you know the sequence, when you know what comes out of each column, you can use Aspen. But you can't just say to Aspen, oh, I've got A, B, and E, please separate them. Right? It can't do that step. It can't design that sequence for you. So you need to know how to design the sequence. Okay? So there's one more technique that we can actually look at to think about separating azeotropic systems. And it's the most complicated one. Okay? So all I'm going to do is essentially tell you that it exists. Okay? So that's what's called reactive distillation. So sometimes it's impossible to find any solvent or entrainer to add to your system that actually gives you a separation you can do by distillation. Okay? But if you add and there's a solvent into your system that may react with one of the components that you actually have in the system, okay? So if you think about running your distillation through potentially a catalyst bed, you can actually react one of your components in the system with a solvent that you've added, okay? And that product may then have a suitable relative volatility to the component that you're not reacting to allow that separation to occur by distillation. Okay? So you're essentially enhancing that separation by reacting one of your components into another component. Okay? Then what you have to do is you have to pick the reaction that's reversible, so you can then recover. So after you've made your separation, you need to do the reaction backwards to actually recover your initial component. Okay? So what we're doing is we're coupling together a reversible reaction with distillation to allow that separation. Okay? So I assume you can now see why I'm just mentioning that this technique is possible, rather than getting you to try and work out how you would actually design such a complicated system. Okay? But I just want you to know that this is a possibility, and that it is a technique that is used, although rarely, in industry. Okay. So we've looked now at how to actually use residue curves and what sequences we can actually use for azeotropic distillations, and then how we can put those sequences onto the ternary diagrams to actually allow us to design the sequences that we want, which we can then take into something like Aspen to do the full design for us.